Hello, I'm Kun Wang, a PhD student from Rutgers University. Today I'm gonna introduce our paper, a recurrent differential engine for modeling Tensegrity robots trainable with low-frequency data. Tensegrity robots are composed of rigid rods and flexible cables, which are controlled by changing the cable lengths. Researchers develop locomotion policies in simulation and then transfer them back to the real robots. However, this process requires a lot of manual effort. To mitigate this issue, we developed a data-driven physics engine to learn transferable policies. However, the frequency mismatch between the observations and simulation raised a new challenge, since the observation may miss important information, such as clearance. The proposed engine includes a recurrent structure, an implicit integration scheme, a progressive training process, a differentiable clearance checker, and finally, a sim-to-sim evaluation with Majoko. The physics engine takes current state and action pairs as input and predicts the next state. The state difference forms the loss function and backpropagate the gradient to update the engine parameters. The recurrent engine will iterate multiple times and predict state t time steps later. To learn a new transferable policy, we first sample non-contact and contact trajectories from Majoko and use them to identify the engine parameters via the recurrent process. After identification, we can learn the new locomotion policy with our engine. Finally, we transfer the learned new policy back to Majoko for evaluation. In details, we first sample the swinging trajectories to identify the non-contact related parameters. Then, we sample the rolling trajectories to identify the contact related parameters. With the identified physics engine, we can learn locomotion policies to roll the robot to the right of the screen. Finally, we evaluate the learned policy on Majoko. We compare the data points of two policy learning strategies, directly on Majoko and with our engine. We find that the training on differentiable engine is sufficient to learn a good controller that is also effective on the ground truth system. The policy includes 5,000 time steps, open loop with 50 controls. The Majoko training policy takes about 100K ground truth data points, while our engine only takes 1K ground truth data points, so which is only 1% of the ground truth policy. Thank you for watching.